Alright, so here's an example of applying Faraday's law. Um, this is actually an example from the AP exam from last year. So I'm not going to go through all of it, just a few questions. But here's our situation. We have a circuit set up like such. It's a square with side L. We have a uniform magnetic field going into the page in this situation, and we have two light bulbs, light bulb 1 and 2, each with resistance R. And we have our magnetic field given by a function B equals AT plus B, which means that over time the magnetic field is increasing. And we want to know, what is the current going around in this loop, which way does it flow, and how much power is dissipated through light bulb number 1. So let's just take a look at this. From my last lecture, when I talked about, or my last my last video, when I talked about Faraday's law and Lenz's law, uh, I explained where this expression comes from. But pretty much the EMF in the circuit is given by, in this case, by dBdt times L squared, because that is the changing magnetic flux in this case. Because in this case, the magnetic field is perpendicular to our surface, so we don't have a theta. Or cosine of theta is 1, and our area L squared is constant, so the only thing that's changing over time is the magnetic field. So if this is our magnetic field, then hopefully you can do this derivative. That's pretty easy. The derivative dBdt is equal to A, and so that means that our EMF is given by A L squared. So we want to know what the current is. By Ohm's law, the EMF is equal to the current times the total resistance, E equals IR. And in this case, the total resistance is 2R, because these two light bulbs are in series, and so the resistances add together, and we get the current is AL squared over 2R. Okay, so that's part 1. Now we want to know, which way does the current flow, the induced current. Well, like I said before, Lenz's law says that the induced current will flow to oppose the change in magnetic flux. Now, in this case, the magnetic flux is going into the screen, and we want to create a magnetic field to oppose that increase. And so in this situation, the induced current would flow in this direction, counterclockwise. Keep in mind, though, that if you had a negative sign in front of this AT, then the current would flow in the opposite direction for obvious reasons. But in this case, the magnetic field is increasing, and so the EMF would generate a current to flow counterclockwise in the circuit. So that's part 2. Part 3 is how much power is dissipated through bulb 1. Well, power is given in a couple different ways. P equals IV, which equals I squared R, which equals V squared over R. In this case, I decided to go with I squared R, and you can see this inside these parentheses here is I square that, and I multiply that by R. And so this term right here is the power dissipated through this light bulb number 1. And in this simple circuit, that would be the same power dissipated through light bulb number 2, because they have the same resistance and they are in series. So that's just a fairly simple example of how to apply Faraday's law. Um, I say simple, but it was one of the questions on the AP exam last last year when I took it. So, um, it's not completely unreasonable that you would see this on an assignment. So, there you go. Hopefully that helps explain how to apply Faraday's law.